So the focus today is two things. One is to learn about binary search because that's part of the assignment that's due on Friday. And then the other topic is vectors, and that's I actually forgot to include that in the list of topics when I first made this list. So we'll cover that. But maybe I need to do something else. Is there any suggestions, or does anyone have a comment about me, what we need to cover now? Any questions? Yeah.
I had a hard time with arrays.
Hard time with what?
Arrays.
Arrays. Well, we're going to work more with arrays right now. All right. So arrays in general. It takes a while. The first sort of hurdle, conceptual hurdle that you need to go over, the main hurdle, is you need to distinguish between the index and the value at that index. That's the main distinction. So you usually have a variable like I, which represents a position number in the array. And then you have the value that's at position I. So the value at position I would be like A square bracket I. So distinguishing those two numbers from each other, that's the main problem that I've seen students struggle with. Let's see, let me make everything bigger. You know, you'll have something like a loop. So you want to go through all the indices. So you start at 0 because the array positions start at 0. And maybe there's some size, there's some total number of positions in the array. Then at the end of the loop, you increment that index. And then inside, you know, for each I, for each position in the array, you can access the value at that position. So use that syntax, A square bracket I. That's the main concept of arrays. That's the core of understanding you have to grasp. Excuse me. But today I want to talk about binary search. And a binary search is a way of finding something in an array. And the array needs to be in an ordered, the elements in the array need to be ordered. And I'll give you an example. So here's an array where the elements are in increasing order. So the size of this array is what? 1, 2, 3, 4, 5, 6, 7. Well, this is a constant, so I'm using, sometimes you see all caps to indicate that this is a constant. And you might do like this, constant int size equals 7. It's not required, but I'm just showing that to you. You might see that actually. It's pretty common. By declaring it const, we can't modify size. We can't do that. Assignment of read-only variable size. So that's an error. Size equals 9. That's because we declared it const. It's just a way to protect the programmer from making a logic error and overwriting a variable that's meant to represent a constant value. Okay. Now look at the array here. Now you can imagine this array, it could actually have 1 million items in it. And you might be tasked with the problem of, okay, well, we've got an array of so many items. Is the number 13 in the array? Right? Is it an unlucky array? Does it have a 13 in the array? Well, we know it doesn't have a 13 in this array, right? Because we could scan across and look that, oh, there's no 13. But what happens if there was 1 million items in the array? And we don't know if there was a 13, it could be anywhere. We'd have to look, if the array was unordered, we'd have to look at every single value to look for the number 13. If we found it, then we found it. If we don't find it, we've looked at 1 million things and we can declare that fact that it's not in there. But if the elements are in order, then there's a shortcut. What we can do is we chop it right in the middle. We look in the middle and we say, well, is that middle item the 13 I'm looking for? And it's no, that's a 2. So 13 is bigger than 2. So that means I can ignore all of this and just focus on looking in this part. This is called binary search. You pick the middle item, and then you decide whether the value you're looking for is in the upper half or the lower half. If it's in the upper half, you can basically ignore the lower half from that point on. Now that in this case, we're looking for 13, so we're going to look in the upper half. So in this upper half, what we do the same thing. It's recursive. It repeats. So we chop this range. We have a range with 3 items in it. We chop it in half. And we get the middle item, which is 12. And we say, is that 13? No, that's not 13. Okay, we didn't find it yet. Is it in the lower half of the range we're looking in, or is it in the upper half of the range we're looking in? Well, it must be in the upper half of the range we're looking in because 12 is less than 13, so it's got to be in the upper half of the range. So this, well, the range is getting pretty small. It started out being 7 items in the range, and then we cut it in half, and we ended up with 3 items. We cut that in half, and now we have 1 item in the range. And we just, because in our code, as a human, we just say that's not a 13. Well, let's get out of there. But in code, we're going to say, all right, let's cut this in half. And the half point is the only point that's in there, so it's 99. We compare 13 to 99, and we say, well, it's not a 13. We didn't find it yet. So is 13 less than 99 or greater than 99? Well, it's less than 99. Okay, so it's less than 99, so we're going to look in the lower portion of the range. But there is no lower portion because we've cut down the range of interest so many times that we only have one element in there. So there's no lower portion. If we terminate the algorithm and we declare that 13 is not in there. So that's it's called binary search. And it's a lot faster than linear search. Well, let's take a look at how that would work. And we're going to implement this as a function. Actually, let's implement it not as a function first. I've never done this before. Let's just implement it right here. We're not going to use a for loop. A for loop is good when you're doing a linear search. If you do, look at the first position, next position, then I is being advanced, from 0 to 1 to 2 to 3 like that. That's good for, a for loop is good for that scenario. But for the scenario that we're in, where we're jumping into the middle of a range and then going to the lower half or the upper half, and that's better for a, for loop doesn't quite express what we need as clearly as a while loop. So we're going to use a while loop. we're going to have some condition in there. So, we know we have to repeat it. We have to repeat something. There's a process. We're chopping the range in half. We're calculating a midpoint, and we're looking at the value at the midpoint. So we're going to have to calculate a midpoint. I'm going to call it M. That's the midpoint, between, I'll say S and E. That's what I usually use, okay? So S is the start of the range, and E is the end of the range. And those are indices. And the midpoint we'll use M to represent the midpoint. So in this example here, this is index 0. That's index 1, 2, 3, 4, and 4. That's a little confusing there. 5, and position 6. So there's 7 items, starting at position 0 and ending at position 6. So we start off with the start point of the range of interest at 0. And the end point of this range of interest will be size minus 1. So we're going to go with the, we want E to be 6 initially, and S to be 0. So S and E, everything's between positions S and E. And we don't want to look at position S or position E. We don't want to look at the value there yet. We want to look at the value that's in the middle of S and E. Anybody know the midpoint formula to compute the midpoint between S and E? Good. You got it. You got it. It's S plus E. It's just the average. The midpoint formula is simply an average. Just add S and E together and then divide by 2. That gives us the middle. It's the average between the two values. Now, once we have this, we're going to look at what's at M. So A of M, that's what, this syntax here, this is how we retrieve the value at M. The value at the midpoint. So if the value at the midpoint, well, it happens to be the value we need to be looking for something, right? So we'll call that K. K equals 13. We're looking for K, which is 13. So if A at M, if this is K, then we found it. Then we declare that we found it. And then we're done. All right, but let's suppose that we didn't find it. Else, if A of M, well, I'm going to do it a little differently. Let's suppose that K is less than A of M. I'm going to reorganize this. Suppose that K is A of M. Let's suppose that K is less than A of M. That means the value we're looking for is in the lower part of this range. So that means we need to slide the endpoint, the end index down. And that's what we do right there. So we're going to create a new, so we know that K is not in the upper half. Everything that starts at M and goes above M, it's not in there. So let's set our endpoint to be 1 before M, because we know that K is not at M. We already checked that here. So we can set the endpoint to M minus 1. What happens if K is bigger than A of M? The other case. k is bigger than a of m, that k is in the upper half. So that means we want to modify the start point. What would the start point be? N plus 1, good. Is there any other possibility here? Can we do this? No, these are, these cover all the cases. This, and this. Those are all, there's only 3 cases. Either k is a of m, or k is less than a of m, or k is bigger than a of m. There's no other case, right? So we should never hit this else. And I'm just gonna, right? So assert false, that'll blow up. That'll terminate the program with an error message. So we should never hit that. I'm just throwing that in for time. I'm not going to leave that into the final code. I'm just throwing it in there just to, as part of the process of thinking through the problem. All right. So it's good to use this. I've been showing you how to use assertions in test code, but actually that's not what they're designed for. They're designed to do what I'm showing you here, which is to insert these statements inside your code that help to verify your logic and your reasoning about the code. So I reason that this else block will never run because I've already covered all the cases already. But just to make sure, I'm going to throw in an assertion so that if my reasoning is wrong, the program will terminate there, and then I'll say, oh yeah, I got something wrong. So that's how assertions are designed to be used. And we're using them in our test code. And that's because I want you to get used to using assertions, actually. So then the thing is, we have to loop. We have to loop until what? We have to loop until, well, we want to loop while the start is less than or equal to the end. Remember when we were positioned on 99 itself? We wanted to continue the loop. We wanted to do this check right here. So we didn't want to stop when S and E were equal. See, when we narrowed into that one item right there, that means S was 6 and E was 6. They were both the same value. S and E were the same value. So we had the case that S and E were equal, so that this condition would be true. That means we would end up doing this comparison, which we needed to do, because what if this was a 13? Then we would need to detect it right here. We would say found at 6. So where were we? Oh yeah, right here, this condition. So when does this condition become false? Let me show you. When S and E were 6, okay, and then this was true, and then this statement, we're going to compare 13 to 99, that would be false. And then we're going to say, is 13 less than 99? Yes. Then E would be set to m minus 1, but what would m be in that case? M would be 6, so E would be set to 5. So now, all of a sudden, E is 5 and S is 6. So the end point comes before the start point. So when we come back to the loop condition is now false. And we exit the loop. So, we can print a message there. Not found. That's what we do. It's hard to see everything, isn't it? There we go. So, any questions? Kind of hard to follow, right? You need to think through it on your own. This is an important algorithm. This is maybe like the first, well, not the first, but this is an important algorithm to understand. So let's go ahead and compile this thing. I think I got it right. I think it's going to say not found, right? Because we're looking for 13. Or K, we set K to 13, and we're looking for it in this array, so it's not found. But let's suppose we set K to 12 or 99. Let's set it to 99. I should find it at position 6. Let's check that. Well, it's found in position 6. It's working. Well, let's set K to 12. So it should find it at position 5. Found at 5. So it's looking pretty good. So we can go through all of those positions. Then we could try a vector that has, maybe instead of an odd number of elements, try a vector or an array rather with an even number of elements, just to get more test code in there to make sure that we got the logic right. So let's do that. But actually, to do this, let's take this procedure that we have and move it into a function, and then we can call the function. So we call the function binary search. I think I named it like that, but we could also name it like this. And binary search takes an integer array and a size and a value to find. I'm going to grab this code, put it in the function. Now we're going to call the function. Actually, let me do it like this. We'll do this a step at a time. So we won't return anything. The functions will print the result. This is not good design, by the way, but we're going to do it like this, step by step first. So we're looking for K. We're looking for K. So we basically just call the function. We call binary search A size and 13. So now our main is a lot simpler. So this should print, not found. Return statement with a value and function returning void. Okay. This should be returned. Size is not declared in this scope. We don't have access to that other size. Now we're going to take the size that's being passed in as an argument. Success. Not found. That's correct. Should not be found right here. But, this function has got, a side effect. What we really want to do is just call this function, have it return the position, see, which is an int, and then we're going to print the position. So we'll do like this. We'll do, we're going to say 13. Well, we'll do it like this. Binary search, it should return a -1. So we're going to return a position. If we don't find we don't find k and a, we're not going to print something in the function. We're going to return a -1. That means we didn't find it. And if we do find it, which is this case here, we're going to return the position, which is m. We found that k at m. See? K equals a of m. So we found k at m. So we're going to return the position m. But if we finish the loop and we never find that k equals any a of m, then we're going to return -1, because -1 is not a valid position index. Valid indices into an array start at 0. So -1 is one before, that. And that's a convention, by the way. It's not just like I invented that now. It's very common. If you have a function that returns a position value, that function is going to return -1 if it can't return a position value to you. Then it returns -1 to let you know it couldn't do what you asked it to do. It couldn't find k and a. That's a convention. So 13 is not in A. So what we want to do is check to see, well, we're going to call this function, we should do it right there. This should evaluate to -1. And so we're going to compare that return value with -1, and we'll say not found. There we go. Let's see if that works. Not found. It does work. And what about trying 99? We should find 99 at 6, right? So 99, we pass in 99, it should return the position 6. See, 99 is in position 6. And so so we'll do 99 found in position 6. There it is. Not found for the first one. Maybe we should say 13 not found, right? I just say not found. Oops. 13 not found, 99 found in position 6. So it's looking pretty good. And I'm just sort of crafting this thing. I like what's going on in here. We don't need this assert. I know it's not going to fail. I'm sure that that's mutually exclusive. This covers all the cases. And in fact, we don't need this if condition here. We could leave it like that. Maybe that's more readable for people. There's other ways of expressing this. I'll show you. We could have done it. We could have done it like this. If k is less than a of m, then return. No, not return. Then if k is less than a of m, then e equals m minus 1. Else, if k is greater than a of m, then s equals m plus 1. Else, return m. We found it at m. So see these 3 lines? That's just another way of expressing this. And there's still other ways of writing it. So that's your judgment. You want to craft the code so that it's easy for you to read, and whoever else is going to read it, it should be as easy as possible for them to read. Now it's nice, I only see 3 lines there, so that's easy. It's less to look at. But is this code, even though it's more to look at, maybe it's easier to read. It's easier to reason about. And let me prove to you that those are identical. And prove to myself as well. That's some proof. It's not absolute proof, but we're getting there. You know, that's getting to be proof. And so I'm just going to leave this commented out for now. That's for you to think about. That's a style, coding style question. What style do you like the most? So now here, we still need to do some visual inspection. I just want to change the test code to put it in a form that I'm looking for, that I would like you to produce as your solution for the lab exercises. Not just this one binary search problem, but for many other problems that ask for test code with assertions. Okay, I'd like to turn these into assertions. So we pass into 13, then it should return a -1. So we're just going to assert that that's the case. See that? When we pass in a 99, it should return a 6. So we don't have to read stuff. These are the automated tests. It's very easy to code these up. And then we can simply run the program. Maybe we'll print all tests passed here. So we want to just be able to run the program, and it just should say all tests passed. We don't have to think anything more about it. Now these, not quite, this is an important problem, so let's be careful with what we're doing here. Let's put all the test cases in there that we can. So that's 1, 2, 3, 4, 5, 6, 7, like that. Well, there's a lot of test cases that we can put in there, isn't there? Maybe more than we really will put in. We're not going to put them all in there. So we could test, between -9 and 4. So we could do something like, make that -13. And between -9 and -4, that would be like -7. That should be -1. And then we have -4 itself. So this is pretty exhaustive here. So 4 is in position, -4 is in position 1. And say -2. -2 is not in there. And then what about 0? 0 is in position 2. I'm being pretty exhaustive. I'm testing that the function works correctly for each value that's in A, and also for every value that comes between every pair of values in A. So that's a pretty exhaustive test. I'm going to keep going. So what's above 0 but below 2? That would be 1. That'll be -1. And what's what about the next one? 2 itself, that should be position 3. And then above 2 but less than 4, that's 3. That should be a -1. And then 4 itself is in position 4. Above 4, less than 12, say 10. That's a -1. And then 12 itself, that's in position 5. And above 12, less than 99. That'll be like in position 13. That was our original test. 99 itself, that's position 6. And finally, to make it absolutely thorough here, we'll test for 101. I think that messed up all my spacing. Oh, I'll just do that. So that's pretty exhaustive, but we could go one more. We could also take an array that has an even number of elements rather than an odd number, but I'm not going to do that. I'm just going to leave it at this. Let's see if that works. All tests pass. We got it. Now keep in mind, if we had a bug in here, let's put a bug in here. Let's do. Let's just do start equals m. Let's see. We didn't come up with that when we were reasoning about the program. Let's see if that's a problem. It might not be a problem. Infinite loop. Look at that. Never terminates. I have to kill it. How do I kill it? Control C. That's an infinite loop. So that one didn't work. I mean, it works, but it didn't show me a failed assertion there, did it? How about if we did this? I'm going to get an infinite loop with that. Got the same thing. We get an infinite loop for that. So how about if we did, instead of minus, let's suppose we did -2 instead of -1. Look at that. Assertion failed. When we tried to find 0, it did not return position 2. It probably returned -1. So then we would say, oh, well, we would check our test code. Did we get the test code right? Because maybe that's where the problem is. But if we're confident with the test code, then we know that we want to look at, re-examine our reasoning about the code that we wrote here. And we might identify, oh, that's the problem right there. Let's go back. So this is, what I'm showing you is considered good practice. You know, writing automated tests like this. This is just standard practice. And then after you get this written, you leave this in here. This becomes part of the software project. You know, maybe there's another program that's going to end up using this function. And that program doesn't incorporate the test code, but you still retain the test code. And you've got this function there is referred to as a unit. And the software project will be comprised of many units, many components, and you'll have automated test code that's written just for testing those components. And you leave it in there. And as the software project evolves, you preserve the old test code and rerun it again, just because you might have a bug that creeps in. And you write new test code as you develop new components, or if you change the functioning of a component, you may need to reflect that in a change to your test code. So that's binary search. And that's due on a Friday, right? This one here. That's in searching here. So first, you want to implement linear search. That's exercise 1. In linear search, the difference here is that in linear search, the items in the array may not be an increasing sequence or decreasing sequence. They might just be random. So you can't use binary search. If the elements are not ordered, then you cannot use binary search. The elements have to be ordered. So in this problem 1, here's test code right there. And there's that example, that array is not in, it's not in increasing or decreasing order, right? Just randomly shuffled. And so you would need to use linear search on that. But for binary search, the code will assume that the array A that's being passed in is in increasing order or decreasing, whatever the case may be here. So I have 2 binary search problems. In this version of the problem, we return true or false. Did we find K in A? True or false? And this is very similar. And this one is the one that we looked at just now. Tell me the position of K in A and return -1 if you didn't find K in A. This is the typical way that you would see the function expressed. But just to get more practice, I'm having you, code both of these up to think about it. And that's it. That's what's due on Friday. It's not too bad. Any questions? Yeah. Exercise number 2. This one? Well, you want to return true or false. Did you find it or did you not find it? Look at the function. Where do you determine? It's hard to see this. Where do you determine that you didn't find it? Which line makes a decision to, which line makes that decision or declaration that didn't find K? Huh? Sorry, 24, yeah. So here, at this point in the code, we know that K is not in A, so we're going to return -1. Well, now we're just going to return false, right? And at what line do we know that K is in A? Huh? 16? Line 16, we know that K is in A here? No. 13. This is the line, this is where we know that K is in A. In fact, we know it's at M. K is in position M in A. So instead of returning M, what do we return? True. We found it. See, it's a tiny change. It's practically, this is really the same algorithm. Just a tiny change there. That's just to get a little bit more experience, a little over thinking about this. Now there's another topic I want to cover, which is vectors. Where is that? Yeah, there it is, vectors. So I'm going to show that to you in this context because we can implement this binary search code using vectors. A vector, by the way, a vector is practically an array. It's just a sequence of values, just like an array. But an array is fixed in its size. You can't make it smaller, you can't make it bigger. Once you declare the array A, its size remains fixed. But a vector is different. A vector has a flexible size. You can append new values onto the vector, or you can take values out. So the size of this sequence can change. And the other thing about the vector that's different about an array is that the vector is what's called a complex data type, as opposed to a primitive data type. A primitive data type is like an int, a double, or a character, or a bool. They take, a few bytes in memory, and that's it. But a complex data type is a piece of data. It's a collection of data. It could be the value of an instance of a complex data type. Its value is based on possibly several different primitive data types. And I'll give you an example. Well, no, I won't give you an example of that. We're going to look at that later, actually. What I want to talk about is how to do this problem using vectors. So here, we would use this syntax. We want a vector of int, so we have to use those angle brackets. So we want a vector, so the angle brackets enclose the type. So the vector, this is a vector that contains int. We could have had a vector of, string, or a vector of char, or a vector of a bool, anything. We can even have a vector of vector. The vector of int. That's okay too. But we're going to, in this problem, what we need is a vector of int, and we'll call that v. We create an instance. This is an empty vector. We're going to create an empty vector called v. And we can only put integers in it, because these vectors, just like arrays, are designed only to hold instances of one particular data type. And we need to include the vector header for this, because the vector is called, it's a template class that's a part of the language, the C++ language, but it's considered part of the library. It's not part of the sort of the core language. It's part of the extended language, which gives us additional functionality. That's referred to as a library in this case. So the vector v, this is very inconvenient, by the way. We're going to need to push. We're going to have to call this function with the dot operator, v dot pushback. So what we want to do is push some values into v. We're going to push in a -9. Then we're going to push in a -4 and so on. So we want to build up, we want v to look just like a. So now v is just like a. So when we here, at this point, v looks like this. It's empty. And then when we push back -9, v will look like this. It'll just be an array, a vector with one dimension, right? Like in math, the word vector is a collection of values, an ordered collection of values, actually. So that's v is. So when we push back -4, see it says back, push back, so we want to add it to the back of the list. So the -4 will come after -9. We push back a 0, then it'll come after the -4, and so on. You get the picture, right? When we get down to the end, v is going to be what will look just like a. Just to keep things simple, I'm going to delete this. So we created the vector. And the vector really is very simple. What's a vector? It's just a fancy array. It's just a fancy array. It's a flexible array. It's an array that we can change its size. And it has these functions that we can call using the dot operator, like pushback, for instance. And so here we're going to call the function, we're going to pass in v instead of a. This is the code assist is not helping much right now. I have to hit escape every time I do this. You know, that's too slow, right? Use the old-fashioned tool here. Let's see how much faster it is using this. And there's an even faster way to do it than this. So, how's that? Oh, look, and it updated it here. That's nice. So we just have to recraft this code so that it works with vectors instead of arrays. Well, it's pretty easy. We declare this first argument as a vector of int. Now, a vector is a complex data type which knows its own size. So we don't need to pass in the size argument. That's a benefit to working with vectors, another benefit. That means we don't have to pass in the size down here. Oh my gosh, the same problem. So that did not work. That worked. There we go. So, so we only have to pass in the vector and the value we're looking for. So the size, we can't use this anymore, right? That's not defined. Well, the size is easy. It's v dot size, but it's a function. So to call it, it takes no arguments. So that's the syntax to invoke a function with no arguments. But you have to use the parentheses. Nothing else needs to change. This notation here, this way to access an element using these square brackets, it's the same with vectors. Arrays and vectors use the same notation. And that's it. That's the only change. The only changes we need to make. Let's test it. Oh, call it V. I don't want to call it A because it sounds like an array. I want to call it V. All right, so let's go ahead and change that. This is going to be V of M, not A of M. V of M. There we go. All tests pass. We got it. See, actually, creating the vector is more cumbersome than creating the array. When we created the array, it was pretty simple. We had very nice syntax to do it all in one line. But for vectors, to my understanding, there's no way to get around having to do it like this, one pushback after another. So vectors are simple. There's nothing complicated about them. Any questions? Now vectors are, after searching, there's an assignment on vectors. And it's very similar to the assignment on arrays. It's basically practicing a skill that you've already learned. So once you learn how to use arrays, then vectors there's nothing much more you need to learn about. So this is a kind of a review. I would call it the vectors assignment is like a review, and just to help you digest this. Like you had mentioned, you had trouble understanding arrays. So I got another assignment in there. This will help you work with arrays even more. So maybe the important concepts will sink in for you with that extra practice. And then after vectors, then we have, what do we have? We've got sorting. putting things in order. Like if you have a sequence of values that are not in order, let's put them in order. That's what this assignment is about. And then we have the next exam. And then there's this topic on classes. And then we talk about application development. So it's almost summer, I guess, right? Any questions? Is there something I need to talk about that? I think that's what you need to know today, right now. Anything else? All right, that's it then. We're done. Okay, good.